Hi, my name is Nima Madian, and today I'll be presenting with my lab mate Graham Turner.
Hi, I'm Graham Turner, and Nima and I are researchers in the mechanical engineering department for Dr. Shima Shahab's Mines Lab. Today, we are presenting our project High Efficiency, Long Range, and Scalable Underwater Wireless Acoustic Energy Transfer. Currently, powering autonomous underwater systems, such as unmanned underwater vehicles, is challenging for persistent and long-range missions. Approaches such as onboard batteries and wired tethering limit the success of this technology. Our solution is to utilize underwater acoustic power transfer and design a system that delivers focused, efficient, reliable, and adaptable power.
Taking a look at the technical problem, we're using piezoelectric effect here to convert between electrical and acoustic energy and vice versa. Electric actuation of an array of piezoelectric ceramic elements allows us to propagate and focus acoustic energy through the water and onto our receiving element, where it's then harvested and stored as a charge in a capacitor. Our project is split into two broad phases. Currently, we're in the first phase of the project where we're working towards benchtop experimentation of the working principles under static water conditions. The second phase of the project will increase the transmission range up to 30 meters and moves to experimentation in larger water tanks under realistic dynamic environmental conditions. A system diagram of the project is shown in Figure 3 in the center of the poster, where we can see the phased array transducer propagating acoustic energy onto the receiver node. The phased array is able to create an acoustic focal point by varying the phase of actuation between its elements such that they interfere constructively at the desired focal location, creating a peak intensity. The receiver node harvests the energy from that focal point and uses it for control, sensing, and processing. A control signal is then sent back to the real-time electrical and acoustic coordination technology, or REACT module, which adapts the driving control of the phased array to improve power delivery.
The receiver sensor node is comprised of four major parts. The harvesting unit of piezoelectric discs connected in an array, creating charge through the piezoelectric effect that Nima described earlier. A power unit that rectifies AC current from the harvester to DC, charges a storage capacitor, and powers the node circuitry. The control sensing and processing unit controls the operation of the node, and the communication unit communicates with the React module as well as other nodes in a distributed network of receiver devices. All of this is pictured in Figure 3. This node network, in conjunction with the React module and the PAT system, enhance the capabilities of underwater wireless power transfer, and these improvements are visualized in Figure 4. Early MATLAB and Simulink simulations for the receiver node device include parametric sweeping of harvester and power unit components to inform circuit topology design and component selection, with an example plotted in Figure 6.
We've also created a robust suite of simulations to evaluate PAT focusing. In Figure 5, we can see three different phase patterns fed to the phased array transducer and the resulting acoustic intensity fields. The middle row here of plots an axial side-on view of the simulation domain, and the bottom row of plots represent a slice of the simulation on the focal plane. The viewing plane is shown on the bottom right corner of each plot. All intensities have been normalized here, and we're using small pressures to observe linear effects. We can see the focal point move from left to right laterally across the simulation domain, and we can shift focus axially as well, towards and away from the phase array transducer. These simulation results are used to inform PAT design and to compare the focusing performance of each embodiment. That's all, and thank you for coming to our presentation.